Section 21.3, carrying on with circular functions. Question 4 says copy and complete the table of values for y equals cosine 2x. Please note, not cos x or sine x, but cosine of 2x. And we go from 0 to 360 degrees. So 0 to 360, going up in 30 degree lots at a time. And I took this one, for example, as a demo at the bottom of the page here, and it says the cosine of 2x means the cosine of 2 times 60, simply because x equals 60 degrees, just there. And so the cosine of 120 is minus 0.5. Again, I don't know that. I asked the calculator. I punched into my calculator cos 120 equals, and I got 0.5, but it was negative. So that's that value there. The cosine of 2 lots of 90 is minus 1. The cosine of 2 lots of 120 is minus 0.5. The cosine of 2 lots of 180 is 1, etc, etc, etc. And then I drew the graph just to save time. Now, I did more than it says in part B. Obviously I drew the graph for part B, but then it says this: compare the graph of y equals cos 2x with what you know about the graph of y equals cos x. So that should really say y equals cos x. And so what I did was, in order to see the difference, was to plot what was required of me, was to draw the graph of y equals cos 2x and compare it with the graph of y equals cosine x. And this is what I got. Isn't that beautiful? Wonderfully color coded as well. So this is the graph of y equals cos 2x in red. Look, it still peaks at 1, troughs at minus 1 at 90 degrees, peaks at 180, troughs at 270, and re-peaks at 360. So that's the graph of cosine 2x. Right? It's a very expanded scale, so you can see the difference. Now, this is the graph of y equals cosine x itself. Look at it. Peaks at 1, cosine of 90 is 0, troughs at 180 as opposed to troughing at 90, and then re-peaks at 360. So let's compare. If you look at the original cosine x, we've got a quarter of a wave, plus a quarter, plus a quarter, plus the final quarter. So we have one complete cosine wave, one complete circular expression of the equation y equals cos x. Now, so that's one wave, the blue one, y equals cos x. Look at the red one. A quarter, a quarter, a quarter, a quarter, and stop. So really what we've got is, for the cosine y equals cos x, we have one complete wave from 0 to 360, but for cos 2x we have one complete wave for only 180. Alright, and it stops there. So it's like it's been squashed in that way a bit. The graph has been transformed, and we will come on to transformation of graphs in the last section of this book. So what have we got then? From 0 to 360 we've got, just follow my pen, one cosine wave and another cosine wave. So there's two complete cosine waves, two complete cosine cycles if we have y equals 2 cos x, and one complete cosine cycle, one complete cos wave if it's y equals cos 1x. So that's it. So from 0 to 360 for y equals cos x you get a complete wave. From 0 to 360 for y equals cos 2x you get two complete waves. And that's it. Do I need to write this down? Let's just do it because I've got time. There's nothing else to do in this video but other than to appreciate the fact that cos 2x produces twice as many waves in the same space from 0 to 360 than does y equals cos x. So let me just write this down in black so it stands out, or maybe thick yellow down here. Right, here we go. So from 0 to 360 degrees there are two complete cosine waves. Y equals cos 2x, as there are there are two complete cosine waves of y equals 2 cos x, not as there are, but really compared with. That'd be better. Compared with one complete wave for y equals cos 1x, and that's it. And that is all this video was about, just to appreciate cos 2x compared with cos 1x, or just cos x. Okay, that's it, and that's the end of our circular trigonometric functions, and very soon we'll be looking at exponential functions, and they're quite interesting as well. Alright, so see you then.